Parsers and printers, like many other functions actually, are intrinsically connected. If we look at the aeson package for parsing JSON as an example, you typically want both an instance of the from JSON class, which takes some JSON text and parses it into a Haskell structured value, and an instance of the toJSON class, which takes a Haskell structured value and sort of renders it back to a string. And ideally, we also don't want the instances of these two classes to be sort of arbitrarily disconnected, but we want certain round-trip properties to hold, right? So if you start, say, from a Haskell value and you render that as JSON, and you then parse it again, you would like to get the same Haskell value back, for example. So nevertheless, right, the aeson package provides two separate classes and thereby suggests that we should implement these classes separately from each other. And many people do. Today, I want to look at a different approach represented by example with the autodocodec package by Tom Sidney Kerkhove. But there are many other instances of this pattern, and it's also not limited to JSON. And the idea is that you have a single description from which you can derive both your parser and your printer in such a way that is more or less guaranteed by construction, or by the setup of that library, that they are compatible with each other and that these round-trip properties hold.
Yeah, welcome to the Haskell Unfolder, a YouTube series where we discuss all things Haskell. As always, the show is live streamed, so we invite you to submit questions or comments in the chat, and we will try to show them on screen and discuss them.
Yes. Okay, before we actually look at this bidirectional stuff, right, let's first look at what we do without it, right? So here is a very, very simple record type with just two fields, an integer and a maybe text. And let's try to define the necessary instances so that we can convert to and from JSON. Now, I think before we even do that, I should say something about generic programming here. I feel a little bit guilty because I'm partially responsible for advocating generic programming. I think one reason why these kinds of bidirectional packages are not more popular is that many people just use generic programming. And how can you do that here? Well, you can say deriving stock generic, right? And then you can say deriving any class from JSON to JSON. And yeah, for that you have to import JC generics and import data aeson. And then you can claim that you're done, right? And then you have a generic JSON printer and a generic JSON parser, and they are compatible with each other. But I think that is most of the time an abuse of generic programming. Why? Because JSON most of the time is part of the external interface of an application, right? As part of your public API. And it's generally, in my opinion, not a good idea to tie your Haskell data type definition one-to-one to how your API looks like, right? Basically, you're then limited and saying, I have to have exactly the fields of exactly the names in this data type for all eternity that are also making up the public API part that corresponds to the JSON of this data type, right? And I think there are usually different constraints that apply to Haskell data types and the evolution thereof and the naming conventions than that apply to the JSON world. And it just, I don't know. I think it's an entanglement that you should usually better avoid, right? But it's tempting to do this because if you want to avoid it, then the standard approach is that you define your own instances, right? And how would you do that? You define an instance from JSON my record where, and then you have to define a method that's called parse JSON. And parse JSON, we can briefly see, is expected to be of type value to parser of my record. Then you typically say something like this is supposed to be a JSON object. You give the object a name, which is primarily used for error messages. And then at this point, you're now supposed to provide something which goes from object, which is like just as value as an aeson specific type to represent JSON objects to a parser of my record. And then you can like basically pick up this object, and you can use some applicative parser where you say make my record applying the constructor, and then say I want to basically parse the field X. So you choose a name here, and I'm choosing, to make the point, right, I'm choosing a different name here than the Haskell record field, just to make it slightly different from the generic version. And then here you have an optional field, so you can do something like, sorry, this is also already wrong. It's this one, and then this one for an optional field. Okay, so that's how the parser could look like. And then you define a toJSON instance for my record, where you have to give a toJSON method. And again, we can look at what is expected. So here we have to go from a value of my record to value, which is one of these aeson specific types. And again, the aeson library provides mechanisms here. So if we just pick up the record, then we have to produce a value. And in this case, we want to produce an object. And there is a constructor in the library that is called object. And then that object expects some kind of monoidal structure of fields, which is called an object. And so we can use mconcat, for example, and then we can say field X is supposed to be the X component of R, and field Y is supposed to be, and again, we can use like a different combinator for the optional field, the Y component of R. And now we don't need GHC generics anymore, so I can. So this gives us also the behavior that we want, right? I mean, we can try this out with these classes. We can do something like encode. Encode is a function that is defined in terms of toJSON. So it's like taking a Haskell value, such as make my record 3 and nothing, let's say. And then we can look what comes out of that. And if we, like, I mean, the default here, as I've chosen it, is that if optional fields are nothing, then they are just disappearing. But there are other options for this as well. And if it's there, then it would be included. And say if I want to test the round trip property, I could just call decode on this encoded value again, and decode returns a maybe of a Haskell type. So I have to annotate here that I want this to be parsed again as a maybe of my record, and that will succeed. And so the round trip property holds, but it holds more or less by accident, right? Because I mean, we had to write code.
I wouldn't call Andrew's code accidental. Sure.
I mean, I don't trust myself, right?
Oh,
and I certainly made mistakes with this before, right? I mean, like probably the very first time you're writing this is not actually the critical point. The critical point is that you're making modifications to your code, right, and sooner or later you're adapting one but not the other. Like in particular, if you're starting to change field names or stuff which is not immediately changing the types involved. So there's plenty of room for error here. So these two functions, parse JSON and toJSON, they look very similar, but they are still different, and they repeat partially the same information. And so, yeah, obviously using generics is much more attractive to some extent, right? But there's a third solution which I think is the best. Like, I mean, the library that I've been picking is one that I've been using a couple of times. It's called autodocodec, but there are other libraries of this as well, for this as well. And I don't want to necessarily say that the other libraries are bad. I think, I mean, for example, there's unJSON, which I've never used, but it looks like very similar. there is JSON grammar, which is an older library which I used to use quite a lot, which I also like quite a bit. But generally, the idea goes much further. And also, autodocodec is, I think, inspired by Tomland, which is a bidirectional parsing library for TOML, parsing and printing library. So the same ideas are not, as I said, are not limited to JSON. They apply to many other situations, just general parsing, printing, serialization to binary code and deserialization as well, right? I mean, so you can imagine many of these libraries. But okay, so let's see how we can do it with autodocodec. So let me comment out the these JSON instances, because we're supposed to replace them. And let me also, because some of the things from aeson and autodocodec are actually named the same, import a much more limited subset of aeson. Probably I want encode and decode as well to run the tests again. So how do we do this with autodocodec? We are, by the way, the name, I'm actually mispronouncing it, I think, slightly. I think the name autodocodec is because you cannot just generate from these descriptions, as we will see, an encoder and a decoder, but also documentation, like a JSON schema or an open API documentation. So I think it is intended to be short for auto-documenting codec. And so I think that's where the name is coming from. Hascodec, so there's a class Hascodec that we have to instantiate for my record now. And again, it's looking quite similar to what we had before, or a combination thereof. So there is a single method here that we have to instantiate, which is called codec. And then we say we want to have an object, which is called my record. And then within here, we have an applicative structure, make my record. And then instead of these fancy combinators, we are using named functions here, required field, field X. And then actually, because it can generate documentation, there is room here to also add some extra documentation. So we can say something like the X field, or some actual text which is used for it, like in a schema description or in an API documentation document for documenting what this field X is actually doing. So that is extra. And then at this point, we have to say how to extract. So this is for the other direction. So you can see that basically this make my record apply to required field is kind of intended to be for the parser. It's mirroring the structure of the parser. But we still need to say how to extract from an actual record value, how to extract the X field. That is the kind of thing that we're doing here in the printer. So we're putting that information here, and we're just using the dot selection. So by the way, I'm using record dot syntax here, but it's not a requirement. It's in line with my recommendations for how to use Haskell records that I gave a couple of episodes ago. But if you don't want to use overloaded record dot, you can do it using classic field selectors as well, right? So, and then here you want an optional field, field Y, Y field, colon Y. Okay. And then
there's one minor comment here which I might as well show at this point, which is that apparently this package can also generate Nix modules.
There are a couple of separate packages built on top of autodocodec. I mean, because you have access to the underlying representation, you can, in principle, define new interpretations yourself as long as you don't need extra information. So that is quite cool. Right, so at this point, you only have the Hascodec instance. You don't yet have from JSON and the to JSON instance. The simplest way to generate that is using deriving via. We have an episode where we used that before as well. I don't want to focus too much on that here, but basically you can now say deriving from JSON to JSON, not generically, not via any class deriving, but via a data type which is defined by the autodocodec library of my record. And that is using the Hascodec instance to now derive the from JSON and to JSON according to this specification. So this is really dependent on having the Hascodec instance. If I comment this out, then the deriving via line up here will fail with error messages that claim that there is no instance for Hascodec, right? So you really need to give this one so that you can then derive the from JSON and to JSON. But if we do this and I get rid of this again, then we basically get the desired behavior in this way as well. Okay, and that's basically it. That's the main message here. That this is a cool approach, and I think sort of it combines the good things about the two other approaches, the two extreme approaches that we've seen before, right? I mean, it has the advantage that the parser and printer are more or less guaranteed to match each other as long as there are no mistakes in the library, in the same way as the generic instance has, but it doesn't couple your grammar, your JSON grammar, to your Haskell data type definition. That you can give a different description, you can do some additional type conversions here, or omit a field and initialize it to a constant on parsing, or do things which are slightly deviating from what your Haskell data type is, and that is entirely fine. So
but I guess all of those things need to be supported by the library, right? I mean, if you want to instantiate to like a default value, if that is not supported by the library, you're kind of out of luck.
Yes, you have to kind of hope that the library supports it, but there's not
a genuine
that
question.
many.
I haven't used it, so
No, there is not that many things that are typically done in JSON. That's one of the advantages of picking such a relatively small domain, that like many JSON parsers fall into a couple of classes, and there are a couple of more advanced features which I'm not showing in this episode, which are very much supported. So you can sort of like do discriminators and stuff like that also with this package, right? So it's not just tied to flat record types as objects as we are seeing here, but that's due to lack of time. Because what I would want to do in the second half is I want to show a little bit of how this is done. And rather than just browsing through the source code, I'm going to try to reproduce a little bit of the code of that package in a slightly simplified way. So it's not like 100% faithful, but we will be able to reproduce this example as well. And it's taking the same general approach underneath. So let me switch to a different module. And we start again from scratch, where we have our data type, which we are going to use as an example. And let's start with the Hascodec class. And the Hascodec class is a class which just has one method, codec, and that is of a data type which is also called codec. And the data type has three type parameters. The first one is instantiated to value. That is the type from the aeson library, right? And the other two are instantiated to a. Now, this codec data type is where most of the action is, and that is actually a relatively complicated and lengthy GADT, which I'm just going to paste in. And we're going to look at it a little bit. And so this is a standalone kind signature in case you haven't seen this before. So basically it just says that you have three parameters of this data type, and they're all just types. The first one is the context type, and the context type is essentially just value or object. Like you could actually make, this is a design choice. I think it's not a bad design choice, but it nevertheless is. Basically, you have slightly different structure for like JSON values, whether you're inside an object or outside of an object. And you could either define two separate data types for describing the object structure and the value structure, which are mutually recursive, or you can, because this is ending up to be a GADT anyway, you can also just join them together and use this value and object thing as a tag, essentially, to distinguish the two cases, right? But almost nothing in here is really overloaded over the tag, so it wouldn't be a huge price to pull them apart. And then you have, for every construct, essentially, in your language, you just have a constructor, so that you can inspect the structure of your specification, of your codec specification as data later, and define different interpretations over it. In particular, for the documentation generation, it is nice to have as much of the structure available as possible. And there are some fundamental building blocks, such as if we just want to encode a plain int or a plain piece of text, we have a direct constructor. If we want to encode an object, we can give the object a name, as we've seen before. And then within, we need a codec for an object. So basically, this embeds a codec for an object into a codec for a value. Then we have two different constructors for required keys and optional keys, and they go the other way around. So like the key has a name, and the key has optional documentation, which we're not going to use in this episode. And then they take a codec for how the associated value with the key is being represented, right? Because, like, I mean, keys don't necessarily need to be flat. I mean, we have, in our example type, we just have an integer and a maybe text, but it could be a nested object or something. So we might want to put a different codec there, right, for the nested data type. So this is why there is another value codec in here.
So is this definition as it is in the library, or is this a simplified version of? It's
a simplified version, yeah. Okay. But it's but these two, for example, these two more or less exist in the same way. I mean, I don't want to.
No, it's just we don't need to look at it.
Let's briefly just show you that it's comparable. So this is a type synonym for value codec. Codec has the same three arguments, and it has a bunch of constructors, and they look similar. There is a little bit more stuff here, but there are more constructors most of all. But it's the same general structure.
Okay.
Right, and then the final three are kind of interesting. This one is sort of, again, this is a really simplified instance that just shows like the only kind of modification of the types that we need. And our small example is a modification of the printer type. Oh, by the way, I've only talked about the context type. The other two type parameters are essentially just say, like, if we interpret the codec as a printer, right, then what kind of Haskell value are we going to print? And if we interpret the codec as a parser, then what kind of Haskell value are we going to parse? And on the outside, like if we instantiate the HasCodec class, they are always going to be the same, because if we're instantiating the HasCodec class for something like my record, we want to both parse a my record and print a my record. But while we are navigating the internal structure, they can sometimes slightly deviate. In particular, within an object, they can slightly deviate because we kind of pass the whole object to the subcomponents to project out the fields when we print, whereas if we parse, we kind of accumulate the object step by step using an applicative structure. And therefore, yeah, we sometimes need to affect the printer types, and there is a mapping function for that in general. And the main package has a full bimap or dimap codec thing where there is some contravariant function for the printer and some covariant function for the parser. Mm-hmm. So we're only using the printer modification. And then the applicative structure, which is primarily used for parsing, is just mapped to constructors as well. So if you look at the types of pure and star in plain Haskell, right, it's something like applicative f a to f of a. So that is reflected here. That's our a, and this whole thing is our f, and that's our a again, right? And the type of the star operator is something like applicative f of a to b to f of a to f of b, and that is reflected in the app operator. Okay, so that's that. So once we have this data type, we can then try to interpret such a codec as a parser. And I'm going to try to, I basically just pasted in sort of the structure of this because it's a lot of typing, a lot of different constructors, but all the right-hand sides are so blank. So for the parser, I'm going to show this step by step. For the printer, I'm going to be a bit quicker. But basically, we're just pattern matching on the codec type, and we are going to implement every case, right? So in every case, we get a codec for a context and the printer type and the parser type. We're getting a context, so that depends. Like if we have a codec for a value, we're getting a value. If we have a codec for an object, we get an object. And then we have to produce a parser of the parse type. We're never using the print type in this function. We're just completely ignoring it. That's the kind of dual to the printer function, which we are going to look at after. Now, in the int and text-based cases, so to speak, we can just rely on the fact that the aeson library, of course, knows how to render an integer as JSON. Parse an integer to parse an integer or parse a text. So we can just use the from JSON instance for these types and just call parse JSON for the value in both these cases. Right. And for the object, that's why I pasted in the comment of how our code looked like before. We want to do something along those lines where we say with object. So with object of my record, that's this T here, but this is a text. With object expects a string, so we'll say text unpack T. And then at this point, I'll need something now which goes from object to a parser. But that's just what parse JSON via codec gives me if I apply it to an object codec. So and I have an object codec here. So I can just call the function recursively to this object codec. And the last argument is this value. Mm-hmm. So this is that. Now the required key codec and optional key codec, that is a little bit different because these combinators here, they're kind of expecting that our fields are already themselves of types which are part of the from JSON class. But here in the codecs, we want to be explicit all the way down. So we actually want to have an explicit value codec. And if you look at the implementation of these methods in the aeson library, you'd usually not write your instances in this way. But this is actually implemented in terms of something which is called explicit parse field. And this is actually implemented in terms of something which is called explicit parse field maybe, which do take these explicit arguments of how to parse the actual field. So we're going to use these two here, right? So
could you not parse it as a value? I mean, the value itself has a
yeah. I mean, that's another trick you could use. Yeah, I would see that as a trick. But yeah, indeed, you could.
Fair enough.
You could. But fine. Yeah, if you prefer that, that's also possible. So explicit parse field, I think, takes 3 arguments. The first one is the parser for the value. So here we're just going to call parse JSON via codec recursively on the value codec. The second one is taking the object. That's the object that we are getting. And the final one is taking the actual key. That's sort of another aeson type for the field name. And again, like we have a text here, which we have to convert. So there is a from text function to convert a text into a key. That's the T. And same for this one. This is explicit parse field, maybe parse JSON via codec val c object from text T. And then the print map codec, actually, yeah, this is only applying to the printer in the limited setting that we have. So we can ignore this here completely. So that's already why I put an underscore here for the function. So we are simply call parse JSON via codec on the embedded codec and on the X. And the app is just mapped to star. So we really just call parse JSON via codec CF on X star parse JSON via codec. And actually, I mean, this is only used within the object context. So this is always an object. So that's probably better via codec, sorry. CX object. And here,
could that not be polymorphic?
if we have a pure, sorry?
Why are those constructors not polymorphic? Kind of seems, maybe it doesn't really matter. I'm just curious.
I think, I mean, you could think about whether you could extend this, but you don't need it really. Yeah. And in the pure case, you're ignoring the object completely. You're just parsing whatever the pure returns. So pure X. Okay. So that's this one. And so the one for the printer looks very similar. And I don't want to go through every case, but if you look at the structure, I mean, so the codec here, we're ignoring the parse argument, right? We're taking something of the print input type and we're producing something of the context type. Again, in int and text cases, we're just delegating, in this case, to the toJSON class and to the toJSON method. And the object case, we're producing an object and then we're calling the thing recursively. And then if you remember, within the object, we're having some kind of monoidal structure, not an applicative structure, where we're, for every field, we're creating some sort of value, and then we're concatenating those values all together. And that is reflected here as well. And that's sort of the nice trick here, that we can use the applicative structure to also build a monoid, because the constant applicative functor is just giving us that, right? If we basically just interpret the star as an append and the pure as a monoidal empty, then we can use the same applicative structure also to compose these printer descriptions. And that's basically it. And perhaps the only other point worth highlighting is that here we're actually using this this function that we're passing around. And now we've implemented an interpretation to a parser and to a printer, and that is the core of the matter. So the rest is basically just boilerplate code. So we have to write a little bit of stuff to make the interface actually nicer, so that we don't have to construct the codec using the constructors themselves. So, for example, we give an applicative instance for the codec, which actually allows us to use sort of the applicative operators in order to build the codec. We define functions, required field and optional field, which are defined in terms of required key codec and optional key codec. We define this colon equals operator in terms of print map codec. That is where that is used. And we define object in terms of object codec. And then we can define our instances. So we need two base instances, which we didn't see before, for int and text, where we just map to int codec and for text codec. But then the instance for my record looks exactly the same as it looked before.
Nice.
And we need to generate a little bit more boilerplate code. Again, I don't want to focus on this again in order to get this deriving via functionality that basically explains how we can generally, once we have a Haskell codec instance, define from JSON codec and a toJSON from JSON instance and a toJSON instance from this Haskell codec instance, namely by invoking the parse JSON via codec and the toJSON via codec function respectively. So this is all very straightforward. And once we've done all this, we can go back to our data type definition of the record up here, and we can say again, deriving from JSON to JSON via autodocodec my record. But this is now not the one from the library, but the one which we completely defined ourselves. And again, we can hopefully verify that if we do an encode of make my record of 3 and say just foo, we get this JSON encoding. And if we decode that again and want it to be a maybe of my record, then it gives us back the original value.
Nice.
Yeah.
There are no questions, but perhaps maybe one thing that might be worth showing is that maybe that deriving via stuff that you showed at the very end is a bit mysterious. If you just delete that and just define the two instances yourself, then you can, I mean, it's very easy to see you're just calling the two functions that we defined.
I can comment that out, and then I have also to comment out this. Then I can define the instance from JSON my record directly, where I say the parse JSON is just parse JSON via codec.
Yeah, which is the function that we defined above, right? That's the one that we started with.
And that's the general interpretation function. And toJSON is the so here I have to
a bit more.
I mean, this corresponds to this code essentially. Here I just call toJSON via codec of the codec.
So we're just calling the two functions that we just defined. And deriving via just makes that automatic, basically. But
you don't have to for every type define these two straightforward instances, and you don't have to remember how the parse JSON via codec and toJSON via codec functions are named. You have to just remember this one new type name effectively, and
cool.
I mean, that's basically it. I mean, I just want to reiterate once more that, I mean, while I think autodocodec is a good library, what I think is really important is the mechanism, right? And this idea that if you have two functions and you want them to be in a round trip property, ideally you shouldn't define them separately. You should find a description that allows you to generate both functions from that description in such a way that the round trip property holds by construction. And that's a very powerful idea. Yeah,
definitely.
Yeah. Okay. No questions, you said. So then I guess, oops, where are you?
That was not very kind.
I kicked extra out.
It's bound to happen sooner or later. All right. Well, thanks everyone for watching this episode. And if you enjoyed it, please like and subscribe. Feel free to leave any comments below. We'll leave the chat open for a few more minutes if you want to have any questions that you can ask now. And I think this is probably the last episode of the year. And I think so too. Probably back second half of January, something like this.
Something around that time, yeah.
But yeah. So see you
definitely not the last episode overall.
Oh no, yeah. No. All right. Thanks everyone.
Yeah, thank you.